Hey guys! In my videos I usually add chemicals to other chemicals, but today I'm going to add an ad. For the first time in over 200 videos I'm finally doing an ad on my channel, and the sponsor of today's video is my own book, The Beauty of Chemical Reactions. This book contains unique photographs of chemical reactions that were specially carried out and filmed for it. Each reaction comes with a QR code. Just point your camera at it and you'll be taken to Vimeo, where you can watch a video of the reaction. This book is really awesome, and as proof, the entire first edition sold out with not a single return. By the way, here are some reviews from happy readers who got the book. So, getting this book is not just a cool gift for yourself or someone else, it's also your huge support for this channel and future videos, and maybe if I sell a few thousand copies, we'll get a camera as good as the slow-mo guys. So, all the details in the link in the description. And now let's get to the video about Dinitrogen Pentoxide. Alright, the first thing we need to do is get some fresh nitric acid. To prepare it, I'm going to heat dry potassium nitrate with sulfuric acid in a sand bath. I've measured out the required amount of potassium nitrate, and I'm now adding the necessary amount of sulfuric acid to it. After that, I stop the distillation flask and start heating the sand bath. I'm using a thermometer as a stopper for a flask. Once the temperature reaches about 85 degrees Celsius, the nitric acid will start distilling over. The nitric acid produced this way is always yellow, since some of it decomposes into nitrogen dioxide that stays dissolved in the acid. You can clearly see the pale yellow drops of nitric acid here. Once the synthesis was finished, we got this flask of yellow fuming nitric acid. Just look at how much this acid fumes in the air. But this acid won't work for producing dinitrogen pentoxide. We need colorless nitric acid, so to remove the yellow color, I'm going to pour it into a 2-neck flask and bubble ozonated oxygen through it. This takes quite a long time, but once the reaction is complete, we end up with perfectly colorless nitric acid. Bubbling ozonated oxygen through it makes the acid colorless, because part of the dissolved nitrogen dioxide gets oxidized into dinitrogen pentoxide, while the rest just desorbs out of the liquid. After that, we need to do vacuum distillation in order to obtain nitric acid with a concentration as close to 100% as we can. To do this, I put together the setup you can see on the screen. It's a regular vacuum distillation apparatus with a capillary tube connected to a reflux condenser where the anhydrous nitric acid vapors will condense. And on the left there is a safety flask with wet alkali to protect the vacuum pump from acid vapors. Under this vacuum, nitric acid is able to distill even at room temperature. However, I decided to use a water bath anyway. The nitric acid distills at slightly below 25 degrees Celsius as a clear liquid. Take a look, unlike the previous synthesis where we used ordinary distillation and the acid turned out yellow, this time it distills as a perfectly colorless liquid, just the way pure anhydrous nitric acid should look. And now, take a look at the setup for producing dinitrogen pentoxide. So first, we need very dry oxygen. For that, the oxygen passes through a wash bottle with sulfuric acid, and then through a tube packed with phosphorus pentoxide before entering the ozone generator. From the ozone machine, the dry ozonated oxygen enters a flask containing a mixture of nitric acid and phosphorus pentoxide. Next, the same gas flow carries the vapors of dinitrogen pentoxide and nitric acid through a glass tube packed with phosphorus pentoxide. Dinitrogen pentoxide condenses in a small receiver flask cooled with dry ice. So, I'm pouring the freshly distilled clear nitric acid into our main reaction flask. After that, I begin slowly adding phosphorus pentoxide to the cooled nitric acid. As phosphorus pentoxide is added, the nitric acid slowly begins to turn yellow and give off brown fumes of nitrogen dioxide. I add phosphorus pentoxide gradually until the contents of the flask turn into a thick, dough-like paste. After that, I put a bent tube filled with phosphorus pentoxide on the flask. This is actually the most important part of the setup for synthesizing dinitrogen pentoxide. And then I'll use a mix of dry ice and acetone to cool down the receiver flask. To do that, I pour some acetone into a Teflon container and then start adding dry ice in small portions, waiting each time for the liquid to stop boiling after each addition. Next, I replace the ice bath with a warm water bath. This helps the dinitrogen pentoxide vapors leave our reactor flask more actively and condense in the receiving flask, which is cooled away with dry ice. For the reaction to proceed well, 80 degrees Celsius is the ideal temperature. After a short while, white needle-like crystals of dinitrogen pentoxide start growing on the walls of the receiver flask. I did my best to find the perfect angle, so you can all see what the crystals of pure dinitrogen pentoxide look like. I hope a photo of these crystals will soon appear on Wikipedia. At room temperature, dinitrogen pentoxide quickly turns yellow as it decomposes into oxygen and orange-brown nitrogen dioxide. Now let's look at our first experiment with dinitrogen pentoxide. I'm going to sprinkle a small amount of these crystals onto a latex glove. When these crystals come into contact with water, they form pure nitric acid, which easily ignites the latex. If you put these crystals on a hot surface, they'll quickly turn yellow and just evaporate away. Like nitric acid, dinitrogen pentoxide easily ignites many inorganic reducing agents. Here's a nice reaction with borosine, the borane ammonia complex. By the way, I filmed this reaction separately for my book, and here is how it looks in it. Pretty good in my opinion. Now I'm going to add a few drops of anhydrous hydrazine to the dinitrogen pentoxide. And here is the reaction of anhydrous hydrazine with human nitric acid for comparison. Interestingly, dinitrogen pentoxide dissolves in anhydrous nitric acid and turns yellow. I've poured a small amount of this cold acid into a test tube, and now I'm adding some dinitrogen pentoxide. As more dinitrogen pentoxide dissolves into the nitric acid, the yellow color becomes more intense. Now let's repeat the experiment with hydrazine, but instead of nitric acid, we'll use what is called nitric oleum. It's not surprising that hydrazine behaves completely differently with such a super-concentrated acid. The latex glove ignited slightly faster than with regular fuming nitric acid. You probably remember how decaborane reacts with nitric acid, but what happens if we add dinitrogen pentoxide dissolved in nitric acid to decaborane? I'm doing this experiment on a fixed ceramic tile. I'm sure you'll share your thoughts on this reaction in the comments below. I just want to thank you for watching and give a big thank you to my patrons who support me in making these videos. It's thanks to you that I've been able to publish many of these reactions on YouTube for the very first time, and honestly, you even helped me get my book published. In short, your contribution to our community is truly invaluable. Thanks for watching, see you in the next video.